Have you ever noticed how rare blue is in the wild? If you take a walk through a forest or a field, you'll see a world painted mostly in greens, browns, and the occasional splash of red or yellow. We see green leaves, brown soil, and bright reds and yellows in flowers and birds. But blue is almost absent. It's as if nature has reserved blue for only the most special occasions. There are no blue tigers, squirrels, or bears. Most mammals stick to earth tones, blending in with their surroundings. Even the blue whale, the largest animal on Earth, isn't truly blue. Its color is more of a grayish hue, and what we perceive as blue is just a trick of the light reflecting off its skin underwater. When we do spot a flash of blue, it's striking and special. Blue creatures seem to glow against the backdrop of the natural world. This rarity isn't an accident, it's a mystery rooted in how color is made in living things. Scientists have long wondered why blue is so elusive. Most animals simply can't create blue. Their bodies lack the chemistry to produce blue pigments, making it one of the hardest colors to find in the animal kingdom. When we see a truly blue creature, it's extraordinary, like a bird darting through the trees, or a butterfly in the sun. These moments feel almost magical. These flashes of blue stand out against the greens and browns of nature, making us wonder how such a vibrant color exists. It's a visual surprise that captures our attention every time. The absence of blue has puzzled scientists for centuries. Why is blue so difficult for nature to create, and how do some animals manage it? Why can nature easily make reds and yellows, but not blue? The answer lies in how color is produced. Most natural pigments just can't make blue. There are two ways: pigments, like paint, which absorb and reflect certain wavelengths of light, and structural color, made from light itself. Some animals have evolved microscopic structures that bend and scatter light to create blue, even when no blue pigment is present. Understanding this difference unlocks the secret of blue's rarity. It's not just about chemistry, but about physics and the way light interacts with matter. Our journey will reveal how animals use physics to create a color biology can't provide. These adaptations are some of the most fascinating in the natural world. Sometimes, the most beautiful things in nature are illusions, crafted with light and structure. Blue, it turns out, is nature's rarest magic trick. Most animal colors come from pigments, molecules that absorb some colors of light and reflect others. For example, a cardinal is red because its feathers contain red pigments that reflect red light. Animals usually get these pigments from their food. Flamingos, for instance, are born gray, but turn pink by eating algae and shrimp rich in carotenoids. If their diet changes, their color fades. This explains most of the warm colors in nature: yellows, oranges, reds, and browns. These pigments are easy for animals to make or acquire, which is why these colors are everywhere. But blue is different. Creating a blue pigment is chemically very difficult for living things. The molecules needed to reflect only blue light are complex and unstable. As a result, almost no animal has evolved a true blue pigment. Nature's paintbox is full of reds and yellows, but the blue paint is almost always missing. That's why blue is so rare. The story of blue is about what nature can't make, and how it finds another way. If animals can't make blue pigment, how do we see blue animals? It's a question that has puzzled scientists and nature lovers alike for centuries. Blue is a rare color in the natural world, and yet, we find it dazzling us in the wings of butterflies, the feathers of birds, and even the shells of beetles. The answer is structural color, a trick of physics, not chemistry. Unlike pigments, which absorb certain wavelengths of light and reflect others, structural color is created by the way light interacts with microscopic structures. Some animals have incredibly tiny, intricate structures on their surfaces that interfere with light waves, splitting and bending them in precise ways. These structures act like a combination of tiny mirrors and prisms, bending, scattering, and reflecting light in a way that produces vivid colors. When sunlight hits them, most colors are canceled out through interference, and only blue is reflected back to our eyes. This is why the blue appears so intense and almost glowing. This isn't a chemical color. It's a physical one, born from the interaction of light and structure. The exact shade and brilliance of the color depend on the shape, size, and spacing of these microscopic structures, which are unique to each species. Change the structure, and you change the color. Even a tiny shift in angle can make the color shimmer or shift entirely. That's why structural colors can look iridescent, shifting and dancing as you move or as the light changes. So, when you see a blue butterfly or bird, you're not seeing a blue substance, you're witnessing a masterpiece of natural engineering, perfected over millions of years. The animal manipulates light itself, filtering out all but the blue, creating a color that is both real and an illusion at the same time. It's a complex solution, but it's how evolution brought blue into the animal world, allowing creatures to stand out, attract mates, or warn predators. Structural color is an illusion, but a beautiful and effective one. Nature's own optical magic trick. Blue in nature's not what it seems. It's a trick of the light, a fleeting moment of brilliance created by the tiniest of structures. And that's what makes it so magical. An everyday miracle, hidden in plain sight. The blue morpho butterfly is a stunning example of structural color. Its wings shimmer with metallic blue, but if you crush them, the color disappears, leaving only brown dust. The blue isn't in the pigment, it's in the wing structure. Under a microscope, the wing is covered in thousands of transparent scales, each with tiny ridges shaped like Christmas trees. These ridges are spaced perfectly to reflect blue light through constructive interference, making the blue incredibly bright. Other colors are cancelled out by destructive interference. Scientists proved this by placing alcohol on the wing. The blue vanishes, only to reappear as the alcohol evaporates. The color depends entirely on the physical structure. The blue morpho is a true master of illusion, using architecture, not chemistry, to dazzle the eye. Its wings are a perfect light filter, crafted by evolution. The magic of its blue is all in the design. Nature's engineering at its finest. Butterflies aren't the only animals using physics to look blue. Many birds do too. In fact, blue is one of the rarest pigments in nature, so animals have had to get creative to show off this striking color. The blue jay, for example, has no blue pigment in its feathers. Its brilliant blue color is actually an optical illusion, created by the way its feathers interact with light. Hold a feather up to the light, and it looks brown. The blue only appears when light reflects off it. This trick of the light is called structural coloration, and it's surprisingly common in the animal kingdom. Tiny, air-filled pockets scatter blue light, while other colors are absorbed by melanin. These microscopic structures are perfectly sized to bounce blue wavelengths back to our eyes. The result is a pure, matte blue that looks the same from every angle, unlike the shifting colors of some other animals. Peacocks take structural color further. Their tail feathers have highly ordered crystal-like structures. These act almost like tiny prisms, splitting and reflecting light in dazzling ways. This creates iridescent blues and greens that shift as the viewing angle changes, making the peacock's display even more mesmerizing. The difference is in the order. Blue jay feathers are messy, scattering light in all directions, while peacock feathers are precise, producing shimmering rainbows. Even our blue eyes work this way. Tiny particles scatter light to create blue without pigment. It's a trick shared by many species, not just birds. From birds to butterflies to humans, nature uses structure to paint with light, crafting colors that pigments alone can't achieve. Each species has its own blueprint for blue, shaped by millions of years of evolution and adaptation. The result, a dazzling variety of blues, all made without a drop of blue pigment. It's a testament to nature's ingenuity. Nature's palette is more inventive than we ever imagined, using physics and biology together to create beauty that seems almost magical. For years, scientists thought no animal could make a true blue pigment. Structural color was the only way. But nature loves exceptions. Enter the olive-wing butterfly, from the genus. Unlike the blue morpho, its blue patches don't vanish when the wing is crushed or treated with alcohol. Chemical analysis revealed something astonishing. The olive wing produces a true blue pigment called nesaiakianin. It's the only known animal to do this, using a pigment family usually associated with greens and yellows. Why this butterfly evolved such a rare ability is still a mystery. It stands alone as the one creature that broke nature's rule. The olive wing reminds us that nature's book is still being written. While structural color's the norm, chemistry sometimes finds a way. This tiny exception highlights just how hard it is to make blue, and why it's so rare. If blue pigment is so hard to make, why did animals bother with blue at all? The answer: vision. Once animals could see blue, it became a powerful tool for communication, attracting mates, warning rivals, or signaling danger. But inventing a new blue pigment was nearly impossible. Evolution, ever the tinkerer, found a shortcut. Animals already had scales, feathers, and skin, so they tweaked these structures at the microscopic level. By changing the size and spacing, they could manipulate light to create blue. This was easier than inventing new chemistry. Structural color became the go-to method for blue in the animal world. Blue is made not by what an animal is, but by how it's built. It's a testament to evolution's ingenuity, solving a chemical problem with physics. Humans have long been fascinated by nature's blue. In the 1600s, Robert Hooke and Isaac Newton studied peacock feathers and butterfly wings, noticing their colors changed with the angle of light. They suspected the color came from structure, not pigment. It wasn't until the 20th century with electron microscopes that scientists saw the nanoscale structures responsible for these blues. Today, researchers are inspired by structural color, using biomimicry to create new paints, fabrics, and screens that never fade. Nature's rarest color is now shaping the technology of the future. The centuries-old quest to understand blue is still ongoing. Every discovery reveals more about the brilliance of natural design. Blue's mystery continues to inspire. The story of blue in nature reveals the hidden genius of life. Blue's rarity is a direct result of chemistry's limits. Nature can't easily make blue pigment. To overcome this, evolution turned to physics, building microscopic structures that manipulate light. From the shimmering blue morpho to the matte blue jay, each animal has its own architectural solution. The olive-wing butterfly stands as a rare exception, proving nature's rules are never absolute. Understanding blue's rarity only enhances its beauty. Every flash of blue is a masterpiece of natural design, a trick of the light that makes our world more vibrant. Next time you see blue in the wild, remember the extraordinary story behind it. You're witnessing nature's most brilliant illusion.